Hello guys, let's go over 10 different questions about probability. Question number 1. Which of the following statements regarding probability is always correct? Okay, so this is a multiple choice question and only one of the answers is correct. Okay, only one. So, and the answer, the question reads as always correct, always. Okay, so only one of these is correct. A probability can range from 0 to 1. Okay, we know that that is correct. Okay, so let's move on to the second one. A probability close to 0 means that the event is not likely to happen. We also know that to be correct. A probability close to 1 means that the event is likely to happen, and a probability of 1 means that the event must happen. So this is correct as well. Now what about choice D? All of the above are correct. We know that A, B, and C were correct, so actually the correct answer to this question is D. Okay, so D is the correct answer. Let's move on to the second one. If A and B are mutually exclusive events, then probability of A or B equals. Look at that. Mutually exclusive events. Where have you heard that? Alright, so let's check the four different options here. Probability of A plus probability of B minus probability of A and B. Choice B is probability of A times probability of B, C probability of A plus probability of B, and D probability of A given B plus probability of B given A. Alright, some of you may have already known this answer. Some of you may intuitively know, but my question here is about mutually exclusive events. My question is, do you have to subtract anything? Do you? As we know, mutually exclusive events are those events that do not have outcomes in common. Alright? Events that are separate. In this case, answer C is correct. Probability of event A or B in mutually exclusive events will be equal to probability of event A plus probability of event B. Okay, we don't need to subtract the probability of both, right? We do subtract that probability of A and B when there is not mutually events happening. Okay. Moving on to question 3. If A and B are independent events, then P of A and B equals. Now we do have conditional probability where you add events A and B. Alright? So it's going to be either A, P of A plus P of B given A, P of A times P of B, P of A plus P of B, and P of A times P of B given A. Now the idea here actually is the independent events. Okay, it's the independent events. And we know that two events are independent, okay, when the probability of event A is unaffected by knowledge that event B has occurred, has not occurred, or there's no knowledge of this event whatsoever. Okay, so these two are independent events when we don't know what's going on, with one of the events, and the results of one event is unaffected by knowledge that the other event has not happened, or we don't have any other knowledge about it. So in this case, independent events, right? P, A, and B. Sometimes you see this intersect sign. This is AND, right? And P and B will be equal to P of A times P of B. Okay, so these are two independent events. So you just multiply these two events independently. Moving on to question number 4. Which formula represents the probability of the complement of event A? The complement of event A. Okay, the complement of event A. Now we do know that rule number one of probability is that probability of event A plus probability of event not A will be 1, right? And you would see sometimes in some books that probability or the complement of event A will be written as probability of A with a tilde. In this book we write it as A bar. Okay, so complement of event A will be A bar. Okay, so the complement of event A is A bar, so A plus A bar will be 1. What is the probability of complement of event A? That will be 1 minus probability of event A. So it's B. Okay, here was B as well. Okay, let's move on to question number 5. Okay, so question number 5. If the probability of an event is 0.3, that means, first let's understand that when the probability is written in the form of a decimal, 0.3, that will be 30%. Okay, so we understand that. Alright, so if the probability of an event is 0.3, that means that the event has a 70% chance of not occurring. If 30% occurred, then what is the probability of the event not occurring? Is 1 minus 30%. So that would be 70%, which is actually answer A, and that is the correct one. You don't really need to go into the other B, C, or D choices because we just found the correct answer. So the event has 70% chance of not occurring when 30% chance has occurred already. So 30% chance occurring, 70% chance not occurring, that would be a total of 1, and that is the total of 2 complementary events. Okay, moving on to question number 6. Now we go into the thick of it. Okay? A recent study of young executives showed that 30% run, 20% bike, and 12% do both. What is the percent of young executives who run or bike? Okay, here's what I'm going to do right now. I'm going to do this. And you know what this is, right? I'm going to visualize it. So why am I doing this? Okay, this is actually a Venn diagram. Alright, so let's see what's going on here. We have 30% who run, 20% who bike, and 12% who do both. So this right here is 12%. This is the percentage of people who do both, run and bike. Okay? Now let's just understand this a little bit. If the 20% who bike, right, are there, and the 12% who do both, what is that crescent here? What is the percentage of that crescent here? Is that going to be 8? Yes, it is. Because 20% who bike, right, minus 12% who do both, that will be 8%. What about this crescent right over here? Okay, what is that going to be? How many percent run? 30%. How many percent do both? 12. So 30 minus 12, that will be 18%. Okay, so that's good. In this case, right, a visual person, right, a visual person would do this. To find out the percentage of young executives who run or bike, they would do 18 plus 12, right, 18 here, plus 12 here, plus 8 here, right? So that would be 38%. Okay, so 38% of people who is the percentage of young executives who run or bike. Now, a formula person all right, would go according to the formula, which is, since we do have a mutually exclusive events that run or bike, right? Because this 12% here is they run or bike events have this 12% in common. Okay, so in this case, what we would do here would create the formula P of run or bike would be percentage of run, right, plus percentage of bike minus percentage, could do both, run and bike. Okay, again, this is intersect, meaning and that'll be percentage of those who run is what, 30, plus percentage of those who bike is 20, right, minus those who do both is 12, and 30 plus 20 is 50, minus 12 would be 38%. So you get the same thing as here. Alright, so the answer to that is 38% of young executives run or bike. Let's move on to question 7. A survey of publishing jobs indicates that 92% are completed on time. 92% of publishing jobs are completed on time. Assume that 3 jobs are selected for study. A. What is the probability that they are all completed on time? Now this may seem a little bit difficult, but it's not. You just have to intuitively understand that these 3 jobs, right, are independent of each other. You have to assume independent events when it is not told specifically that these events are not independent. So these are independent events. Okay. So if these 3 jobs are independent of one another, then we have the probability, okay, of 3 jobs written as 0.92 times 0.92 times 0.92. All right. Probability of A times probability of B times probability of C. Okay, and that would be 0.7787 or 77.87%. Okay, so it's that easy. You just multiply these 3. Now, here's another idea. You can always be slick and play devil's advocate here, because imagine that you did not want to do the multiplication. What happened if you add 0.92 to 0.92 to 0.92? This is going to be greater than 1, right? And we know from the rules of probability that probability cannot exceed 1, right? So now you cannot do addition, therefore you must do multiplication. Is that easy? All right. B. What is the probability that at least one was not completed on time? Now this is a little bit difficult, but let's understand this. Here you have to apply the rule of complementary events. What does it mean, at least one? At least one is a complementary event of none, right? So probability of at least one will be 1 minus probability of none. You understand that? So probability of none would be the complementary event of probability of at least 1. These 2 are opposite events, right? So probability of none plus probability of at least 1 would be 1. Okay, at least 1 job will be 1. Now, that's another thing here that we need to understand. None were not completed on time. Were not completed on time. Alright? So none were not completed on time is double negative. None and not. That means that is equal to all were completed on time. Alright? A double negative, none were not completed on time, is equal to all were completed on time. all were completed on time is this probability. Probability that they are all completed on time is 0.7787. Okay, so now we would find out probability of at least one, right? Probability of at least one will be 1 minus 0.7787, because probability of none were not completed is the same thing as probability of all were completed. Okay, so now that probability of at least one will be 0.2213. Okay, so now 0.2213 plus 0.7787 will be 1, and these are two complementary events. All were completed on time, and at least one was not completed on time. Okay, let's move on. Today's local newspaper lists 20 stocks of local interest. Of these stocks, 10 increased, 5 decreased, and 5 remained unchanged yesterday. If we decide to buy 2 of the stocks, what is the likelihood that both increased yesterday? Okay, both increased yesterday. So this increase will be associated with these 10 stocks that increased. Okay, and we need 2 of the stocks now. We need to buy. And when we say what is the likelihood, that means what is the probability. Alright, so in this case, probability, actually stocks, can be understood to be without replacement. So if we buy 1 stock, right, that stock doesn't go back into the 20 stocks. Alright, so then the sample space will be 1 stock less, right? So unless you were told that there is a replacement, infer without replacement. Okay, so now we're just going to go on without replacement. So the probability of both increased, alright, will be what? These two multiplied. So these fractions. The first one is 1. How many sample space do we have? How many total outcomes do we have? We have 20 stocks, right? Now, how many increased? How many favorable outcomes do we have? How many possible successes can we have? 10, right? So this 10 is those who increased, and this 20 is the number of stocks that we have. Now, when we buy 1 stock, now from the increased, we have 1 less increased and 1 less stock in all, right? So now the total possible outcomes, sample space decreased by 1, therefore we have 19 here, and then we have 9 here. So that would be, right, 90 over 380. And then you can change that and make it a decimal, or simplify the fraction, or give it to me in percentage form. Okay, let's move on to question number 9. This is a little bit easy. Okay, let's say that 6 employees of a marketing firm had effectiveness ratings as follows. Okay, 0.72, 0.46, 0.59, 0.64, 0.81, and 0.76. Find the probability of selecting an employee with the indicated effectiveness rating as follows. 1 is greater than 0.75. How many of these ratings are there? Probability of event A greater than 0.75 will be in this form. Fraction, right? How many total possible outcomes are there? 6, right? And how many of these ratings are greater than 0.75? Is this 0.76, 0.81, and that's it. These are the only 2. So it's 2/6 or 1/3. Okay. Now let's move on and find out the probability of less than 75 but greater than 0.5. So probability of event A, right, that is greater than 0.75 but smaller than 0.5. What is that going to be? Over 6, what do we have? Out of 6 total possible outcomes, we see that the greater than 0.5, right, but smaller than 0.75 is this, is that, 0.72, 0.59, and 0.64. Okay, so 0.59, 0.64, and 0.72. How many of those are there? 3. So it's 3 over 6 equals 1/2, or 50%. Okay. This is 50%, right? And this is 1/3, or equals to 33.33%. Approximately then. Okay, third, greater than the mean. Now this brings us to what? To chapter 2, to measures of central tendency and mean mu, or x bar for sample. Now we need to really find out the mean here. The mean, x bar, right, is equal to sum of all values divided by the number of the values. So number of values is 6. The sum is whatever sum is, but the mean will be approximately 0.66. Okay, so now the probability that the event A, right, is greater than 0.66 will be, out of 6, we have 3 values, or effectiveness ratings that are greater than 0.66, so that will be 1/2, or 50%. What about this now? Not less than 0.9. Now, I like to understand this and make it simple by just removing this not for now. So less than 0.9. How many of those are less than 0.9? There are 6 over 6, which is 1, meaning all of them are less than 0.9. Now, what about not less? Not less would be the complementary event of this. So 1 minus 1 would be 0. So not less than 0.9, probability of not less than 0.9 will be 0%. Okay, because all of them were not, none of them were not less than 0.9. One more question. A market analyst is hired to provide information on the type of customers who shop at a particular store. A random survey is taken of 100 shoppers at this store. Of these 100, 73 are women. The shoppers are grouped in 3 age categories, under 30, 30 up to 50, and 50 and over. The data is summarized in the table on the right. This table right over here. Okay, first of all, women and men, gender is a nominal variable. Okay, under 30, 30 and 30 to 50 and 50 and over is what type of variable? You already know this, but I'm going to tell you anyway. This is an ordinal variable because these categories are ranked from lowest to highest. Okay. The conditions here are that let W be the event that a randomly selected shopper is a woman, so W is a woman, and A be the event that a randomly selected shopper is under 30. Okay, so under 30 and women are the 2 events that we're going to work on this exercise. Question A. Find the probability of W bar. W bar is the complementary event of W, which will be 1 minus W. Okay? Now first, this is going to be called probability of not a woman. Okay? So probability of not woman, which is probability of W bar, will be the probability of men. Right? So what is the probability of men now? Probability of men in this case will be out of 100, which is the sample space, right? How many men do we have? 27. So that will be the probability of not woman. B, find the probability of A. Okay, probability of A. A was the event that the randomly selected shopper is under 30. Okay, so probability of A will be out of 100. How many under 30 do we have? 38. So that's going to be 38 over 100. Okay? Question C. Find the probability of A and W. Okay, so now probability of A and W, again this is the intersect, that's how it's written. It's the same as probability of A and W, right? Probability of A and W. A intersects W. Alright, so the probability of A and W will be equal to probability of A times probability of W. Right? And in this case, we don't really need to use the formula here at all, because we can have the table, and anytime you have a table like this, right, just go on and look at the table, and the table is asking us what is the probability that the shopper is under 30 and a woman. What is that? 30, because that's the cell that intersects these two events. Okay, so now that's going to be 30 over 100. Good. D. Find the probability of A or not W. Okay, so now this is going to be written as probability, right, of A or not W, or W bar. Now you see this? This is OR sign, and intersect is that. So whenever you see this sign, that is AND, and whenever you see this sign, that is OR statement. Okay? So probability of event A or not W, right, will be equal to, now we have OR, so we have to add probability of event A plus probability of men, because not W, right, remember here, was probability of men, minus probability of A and men. Let's count that. Probability of A. What is the probability of A? We have it right over here, so it's 38 over 100 plus, what is the probability of men? We have it right here in question A, so that is 27 over 100, right? Minus probability of A and men, meaning we do have the probability of men who are under 30. Okay, so A was the probability that is under 30, and men is right here, so men under 30 is 8, so minus 8 over 100. Okay, so that's going to be a probability of 57 over 100 and equals to 57%. So that's the probability of A or not W, meaning men or under 30. E. Find the probability of A given W. The word given. The word given is reminds you of the conditional probability, right? So that's going to be probability of A given W. That's how it's written, right? So how is that going to be? Whenever you have that given W, right, is given women. So in this case, what's going to happen here is that in the table, right, we see this. By the way, this number here is 8. It was written 25 by mistake, but that's an 8. right? Okay, so now when you have the word given, means that you really have to look at the column of women, right? So that's where you look at. This is it. So given women, 73 here, right? How many of those are under 30? Because probability A is event that those are under 30. So how many of those are under 30? 30. Okay? So that's going to be 30 over 73. Okay? That's going to be close to 41%. So the word given actually shrinks the sample space. The sample space is 100, but when you are given only one of the categories, for example women, then you have to look at how many women are there in total. And within women, you have to really find how many of those are under 30. Okay, so shrinking the sample space, finding the correct category, and then doing the fraction. 30 over 73. Okay, 30 over 73. Last question, F. Test for independence of A and W. Test for independence of A and W. Being under 30, A is being under 30, and W is being a woman. Now we do know, right? Let me just erase these. We do know that to test for independence, we really need to find out, right, if probability of one event A is going to be equal to the probability of that event A, given that event B has happened, right? So in this case, probability of event A should be probability of event A given W. Probability of event under 30 will be equal to the probability of event under 30 given that that event woman has happened. Now we already know probability of event A is 38 over 100. Is that equal to the probability of event A given woman, which is 30 over 73? No, it is not. No, it is not. Right? So this is different. This is different. This event and this event are different. Therefore, these are not two independent events. These are dependent events. Okay? So remember this formula in order to test for independence. Okay, good luck. Don't forget to do your assignments.